In this video, we're going to talk about binary search trees. We will start from definition and then implement the insert function in the binary search trees, delete function from the binary search trees, and also we will implement a checker which will check if this binary tree is a binary search tree or not. The binary search tree definition is this is a binary tree in which for every node the all left subtree nodes are smaller and all right subtree nodes are greater. And let's start from inserting function, and we will write its type signature. So insert. Okay, first of all, let's look at our tree definition. I will use a pretty print module which I implement in one of the previous videos. You can find this video in the description, and also the code of this video. So it prints tree like this. I will use it for better illustration of what we do. So this is our definition of the tree. I will copy it and put it here. Okay, type signature. They have this some bit tree of type A, and they have some A value which we want to insert, and we will produce a new binary tree of type A. And this is all. Let's start from some corner case if we have an empty tree. So we constructed this constructor, empty constructor, and we have some value. In this case, we just create a tree with this value A and empty subtrees. Otherwise, if we inserting the node which contains some value V and left and right subtrees, okay? In this case, if our A is less than our V, then we need to construct a new tree. So it constructed with our node, and we leave it the same for our vertex V, and because this insertable node A is lesser than our V, we need to insert it to the left. Okay, and we recursively define it like this. Insert to left subtree our A, and the right subtree stay unchanged. Otherwise, if our node if our A is greater or equal than D, in this case, we insert by definition, we insert it to the right, okay? So the root stay the same, this is V, left subtree stay the same, and we just built another right subtree. So, and this is, I think, all. This should work. So let's start GHCI, load our module, go HS. Okay, some errors. Of course, because we do compare here, we need to define our A as a subclass of ort. So this is an ort type class. Here we need this constraint for our function. And now it's loaded. Okay, and now let's try to build some tree. Okay, we will start with nodes 1, 2, 3, I think. And we can build our tree fold left function, fold left, and we will use our insert function to fold this and empty tree as a start tree. Empty tree as a start tree. Okay. Let's try to run this. Okay, and we can see that we have some tree here. Let's pretty print this tree to visualize this thing. So we have print tt function, and we want to print this thing. Okay, and you can see this tree, and this is a binary search tree. You can see that every node from the right is greater than our observable node. So let's add some numbers here. And see it again. Okay. You can see that here we have also binary search tree. All our conditions met for every node. Now let's define the delete function. As always, we start from type signature and it exactly the same. So we have some initial tree, some deletable node, and we will produce a new battery. Of course, we will start from empty case. If we have empty tree, and no matter what we're deleting, we can delete this from empty tree, because empty tree stay empty tree. But if we have some node, and now we want to delete A from it. Of course, at first we need to compare our A with V. And if it equals, this means that we find what we want to delete. So we need somehow mark this. If we have equal, we need to take rights one of the subtrees. Okay. So, for example, if the from this tree, we want to delete 2, and we found this. Now we need to delete this 2. Okay. So how we can do this? We can take this right subtree, this left subtree, and when we take this right subtree, we need to find the minimum element here. And to find the minimum element here, we need to always go to the left. So here we can see that we take 3 and we try to go to the left and nothing here. So 3 is a minimum. and every node in the left subtree is lesser than this minimum, because all right nodes are greater than 2. So we take this left subtree and attach this here. So we need to reconstruct, okay, this tree started from here and add 1 to here to the left, because we can't move left anymore. Okay, let's do the implementation of what I say. So if we found equality here, we need to do some sub-insertion. I will call this left subtree insertion to the right subtree, sub-ins. And we take our right subtree, and into this right subtree, we sub-insert this left subtree, okay? And but what if our v is less than a? This tell us that we need to reconstruct our tree. The node v stay at its place, and left subtree stay the same. This tell us that we need to delete our node A from the right subtree, okay? Because left subtree does not contain it, because we have LT here. It's somewhere from the right. And in other case, if we have greater, if our v is greater than a, this means that we need to modify left subtree to remove our a from the left subtree, and right subtree stays the same. So finally they need to implement this sub-ins function. And let's start from simplest case. Sub-ins empty. When our right subtree, in this example which we talk about, if this right subtree was empty, that means that we just create our left subtree as it is. And if our right subtree not empty, this means that we need to move to the left, and this looks like this. So we always move to the left here, and once they can't move, then we have empty tree, okay? And in this case they just put left as it is. So you can see that sub-ins is try to modify left subtree here until it find, and it just keep it the same until it find the empty tree. And if it find the empty tree, left empty tree here, it just change it to itself. Let's try to compile this thing. Okay. I have number of arguments mismatch here. Of course, here I forgot to put L subtree. And it's done. So let's try to build some tree. And then let's try to delete from this tree. We will delete, for example, let's delete 4, okay? And you can see that we have this tree, and then we delete 4. Our tree stay the binary search tree again. So now let's try something else. Let's try to delete 2, this root from here. Okay, if we delete 2, we can see that our left subtree moved to minimum of this right subtree. Let's try to delete 7, I think. 7. Yes. And let's try to remove 3. So if here we remove 3, okay, this is a simple case shown here. And that's all, I think. I hope that I didn't do any errors here, logical, and this should work. And now let's implement the check function. So check function. It's type signature. So it takes some battery of type A and produce a boolean. So it's this tree either the binary search tree or not. And of course we need to ord type class constraint for our A, because we need to compare our nodes. And how can we implement this? So I want to do implementation exactly like the definition. So much closer to definition. I found some implementations in the internet and they so far from this definition. But I want to do this exactly like defined here. So to start, I need at first to make our battery instance of functor and instance of foldable. So I will do this now, and let's start. So instance foldable battery. So I will start, I think, from functor. Yes. Instance functor battery. There. I need to define fmap with some function. I will start from simplest case, then they have empty tree, then nothing to change in it. But if they have some function f and some node with value v, left, right, subtree, subnodes, And now we can change this v with our function f, and we need to reconstruct tree, and also we need to fmap our left and right subtrees. And this is all. I think this should work, and let's check this. So to check no implementation, let's do it undefined. Let's reload. And our tree is a functor now, so this means if I have some tree here, I can do some modifications of this tree. Okay, for example, this tree I can modify it by multiplying at 10, by multiplying at 10 every node. Okay, you can see that this thing works. And then next I need to do an instance of foldable. Oh, instacar. instance of foldable battery. Okay, to do it in instance of foldable, I can go in two ways. The first way is to implement the fold map. Let's see at the foldable. So we can see to implement foldable, I need to define either fold map or either folder. So, and I will do both of them here. So I will start with fold map. Fold map. If we have empty tree, then this means that nothing to fold. Okay, let's we can see here in our definition, in our type signature of fold map, that they need to provide some t of a. This is our tree which contains a's, and then they need to provide some function from a to m, and m here must be monoid, and because it is monoid, we can fold all these tree, all these values with the append or function of monoid, and they will receive the monoid here. And if they have empty tree, then nothing to fold, and this means that we need to return to define our fold map as empty of monoid m. And if our tree not empty, we have some node v left and right subtrees, we need to apply our function to our node v, and v will receive some monoid value, and we need to combine this monoid value with all with all folds from the left and all folds from the right subtree. So we go to recursion here. We take our left and right subtrees, fold map them with our fold map, this thing give us monoid instances here and here if we just combine them with our monoid. So, and this is all. This is our definition. And now when I implement this thing, let's try to reload. It's done. We have now our tree, the instance of foldable, and this means that I have all this function for our tree. So I can check for LM, maximum, minimums, I can sum, I can product, and I check length. Can check length and check for null again. So, and this is nice. But now let's return to our check function. So I start to implement it here. Let's move it. Let's move it here. So check if we have an empty tree. If we have an empty tree, this means that our tree is binary search tree, I think. Why not? Binary search tree can have no elements in it, and it will be a binary search tree. So, but what if we have node and left and right subtrees? So I say that I will do this implementation closer to the definition of the binary tree. The definition is for every node, all left subtree nodes are less than this node, and all right subtree nodes are greater than this node. So this means that I need to check all with my compare function. So I must all the nodes check with greater function, apply to our node V to the left subtree, and check all the nodes with some function. I didn't know how to implement it yet, but I will do it later. I need to compare that all right nodes from right subtree are greater than the. And also I need to check this condition for every node from the left and every node from the right. Okay. And one thing I need to do is to implement this strange all function. And this function takes some condition here, which compare with my v value of the root node, and it takes some binary tree. And what we do at first? At first we take our tree branch, and we fmap it with this function f. So it can be like this or like this. We fmap it, and our tree transferred to tree of booleans. And we need to take all these booleans and check that all the nodes are true. Okay, because we want this condition holds for every node. So how can we check this? Okay, of course we can check this with folder function. So we take folder, the logical end for fault, and true we take for initial, and then we take our tree as foldable. And this thing will give us the answer that all the branch is greater or smaller than this node. And that's what we need here. So let's try to recompile this. We can see that this is compiled. And now I want to check, for example, this tree is binary search tree or not. Okay, some exceptions. Undefined. Okay, the problem was that I didn't reload the model, I think. Or reload. Okay, then I reload, it start to work. Okay, let's check, and we can see that our testable tree is binary search tree. You can see through here. So, and what if I modify this tree and transform it to not binary search tree? For example, I will create some node with some big value 100, and from the left I will make empty tree, subtree, and from the right I will make this tree with values less than 100, and in this case this will be not correct binary tree. Okay, let's print it. And we can see this is not correct binary tree because at the right we have all values lesser than 100. And let's check this. Check. Sorry. I need to remove this print here, of course, and check. And we can see that this is a false. This is not binary search tree, and it works. So guys, thanks for watching. Push subscribe, push like, write comments, and see you in the next video. Bye bye.